Okay, again, the next example now is number 10 in the exercises, okay? Now, according to the information they give us there, we want to invest $2,000 to begin with, okay, the principal amount. Interest is going to be compounded 12 times in a year, so every month. And the interest rate is given as 0.25%. We're going to have to change that to a decimal. And they want to know how much is going to be in the account after 8 years. Okay, so that's part A. There's two parts to this. Part A is find out how much in the account after 8 years. Part B, I think we'll set that up as a separate video from this one, just because the whiteboard can't hold that much. Okay. Notice I've got the correct compound interest formula. Gang, I'm going to drop all of these numbers in there. Okay. Okay. Next, I want to find this. All right, so we just, simply put, we just take the number 8, plug it into the expression or the variable t right here, and all of this into the calculator. It really is as simple as that. Sometimes the problems are a little tricky. Look, I ain't going to deny it, right? But for this particular one, it's just a matter of plugging in the 8 and then forcing all of this stuff into a calculator. And when you do, it winds up being, I got this much. Okay, so again, with your calculator, take 8 years, plug 8 into the t right here, everything into the calculator. That'll take care of that. I think, again, maybe we can fit letter B here. Letter B says, solve this equation. Okay, solve this equation for t. You know what that means? Gang, what they're saying is replace the symbol A of t in this formula with $4,000. What they want to know is how long is it going to take for your principal amount, $2,000, to double? Now you got to be careful. This is not compounded continuously, right? You can't use logarithm of 2 divided by the rate. That doesn't work for this one right here. We're actually going to have to do the math for this one. No big deal. It's just a little on the tedious side, but we can do it, okay? So I'm going to replace, in this formula right here, I'm going to replace the left-hand side with $4,000, and then we're going to solve the resulting equation for the t right there in the exponent, okay? So again, here's what that's going to look like. Okay. In the interest of space, okay, all of this stuff right here on the inside, I'm going to use my calculator to figure that out. Usually it's better if you can fit all of this stuff into the calculator and just make one calculation, because there's always going to be some kind of rounding error if you don't. But I'm going to do it again in the interest of space on the whiteboard over here. There's just not that much, gang. So the stuff on the inside of the parentheses, 1 plus 0.0025 divided by 12, that winds up being this. Okay, and there is some rounding there. All right, so when we compare our answer to the answer in the back of the book or the end of the section, it's going to be off by a little bit, and that's the reason why. Okay. All right, so I want to solve this equation here for t, which is currently in the exponent. So kids, the first thing I'm going to do is I'm going to divide out the 2,000 from both sides. Okay. Then I'm going to appeal to that very special relationship we discussed back in section 6.1. Do you remember that? Remember this? How we said that those were equivalent equations, gang? So what I'm going to do is I'm going to rewrite this one in terms of its equivalent logarithmic equation. Why did we do that? We said because, well, first of all, if we always do it that way, we're never going to lose sight of that relationship. It's like we're practicing it all the time, okay? The other thing is what we're hoping for is some kind of insight, right? When we replace one equation with the other, what we're hoping for is some kind of insight, how to proceed going forward, right? And that's going to happen actually with this one. The equivalent logarithmic equation for this exponential equation is going to be this. Okay? Now, is there some insight to be gained here? Actually, I think there is. Because look, there's t right there. Divide out the 12 from both sides. Okay? Okay. Now look, don't let that throw you. I know that's a funny looking base down there. Don't let that throw you. First of all, we've got scientific calculators. How often do we say, gang, our scientific, none of this stuff frightens us, right? What I'm going to do for this one right here is I'm going to use the change of base formula so that those of you that have, like usually the Texas Instruments calculators require us to use change of base because they can only do common logarithms and logarithms base e. It's no big deal. It's an extra step, right? Come on. So this is the same as the following. Okay, and then all of that divided by 12. Okay, it's one extra step, like I said. All right, now with our calculators, this winds up being t equals. Let's see. It's quite a long time, all right? But t is equal to about 275. Okay. So again, this is number 10. So the previous example was the interest was compounded continuously. For this one, the interest was compounded a finite number of times. That's why we had to use the different formula. Okay. And then after this one, we'll see an example maybe of exponential growth and decay as it pertains to something other than compound interest. Okay.